So we're going to look at another visual representation known as scatterplots, and then correlation as well. So this is all to do with bivariate data when we're looking at two different variables for the same data set to see if there is some relationship between these two. So that relationship we call the correlation. So the scatterplot graphs the bivariate data. So the example I'm using here is yearly examination results from a particular year. Now, my first graph is how did students go in mathematics extension versus mathematics itself. So only the students that did both of those exams. And so we plot based on their two scores. This particular scatter plot, we can see that they're all clumped together. If I was to plot English Advanced versus English Extension, we get a slightly different one, but they're still reasonably clumped together. Well, what about Maths Extension versus English Extension? There's no reason why those should be related to each other, and you'll see that that scatter plot has now spread out a bit more. Here's Maths Extension versus a completely different subject, Business Studies. And again, you can see they're wide apart, all the different points. Finally, Maths Extension versus PDHPE. Now, the correlation will tell us the strength of this scatter. And a correlation will always fall between -1 and 1. So all right, let's have a look at each of these individually. The very first one we looked at had a correlation of 0.81. And that's a very strong correlation. And you would expect that. We're comparing two similar subjects, mathematics and mathematics extension. We would assume we'd achieve similar results in both. Now, the English Advanced versus English Extension, 0.49 is their correlation here. So that would be a moderate relationship or a moderate correlation. 0.23, the Maths Extension versus the English Extension, and that's a weak correlation. So you can see as they get stronger, going from right to left, the data becomes more clumped together. Now, the Business Studies and the Maths Extension there, that has a correlation of 0.01. So there's virtually no correlation at all. And the PE versus the Maths actually has a negative correlation. So same as any graph. You put the independent variable on the horizontal axis and the dependent variable on the vertical axis. With bivariate data, it's not always clear which one's independent and dependent. And if that's the case, then it really doesn't matter which one you put on the horizontal and which one you put on the vertical. We're concerned with linear correlation, but it is possible to have nonlinear correlation. Let's just have a look at some of those. Here's one which would have a strong exponential correlation. So we can see the data's moving like an exponential curve, and they're all grouped together. This would have a strong inverse correlation. It looks very much like the hyperbola, and again, they're clumped together. And the third one here, I don't know what that data would be, but it would have a strong quadratic correlation. We can see it looks like a parabola. All right, we're concerned with linear correlation. Now, a single line that represents that pattern of all those points is what we call a line of best fit. Now, it's important that you identify any multiple points in the scatter graph using large circles or something like that, because the number of times a particular piece of data occurs could affect the shape of our relationship. So other shapes, it doesn't have to be a circle, you could use triangles, other shapes like that, or simply placing the number of times that that piece of data occurs inside the point itself. So let's go back to our Maths Extension versus Maths. So if the correlation can clearly be seen, like our example, then we could draw a line of best fit by eye. And so I've attempted to do that one there. Now, assuming that the data is reliable, we can now make predictions. We could interpolate. Now, interpolation is predicting results within the range of data. Now, the range of our data here goes from, I don't know, what's for Maths Extension, the smallest score looks about, 25% maybe, and the highest one, 99. So I could interpolate that a student scoring 40, because that's within our range of data there, a student scoring 40 in extension, I could go up to my line of best fit, read off the horizontal axis, and 70% we would expect that they would score, or we would predict that they would score in 2-unit. Extrapolation, or to extrapolate, is when you predict outside the range of the data that you actually have. So in this case, well, we didn't have anyone scoring down at 20%, but I could extrapolate from our data that someone getting 20% in extension, they would probably get 60% in the advanced course. So that's the difference between extrapolation and interpolation. Interpolation is when you're predicting within the range of your results. Extrapolation is when you're predicting outside the range of your results. Now, this brings up a really important point, the difference between correlation and causation. Just because you have a correlation doesn't mean it's true. Show you what I mean. During summer, people get hay fever. There's also a lot of pollen in the air during summer. There's a strong correlation between the presence of pollen and hay fever. So therefore, can we conclude that pollen causes hay fever? Well, that's a sensible correlation because there have been lots of studies that prove this to be true. Let's give another example for summer. During summer, the sale of ice cream increases, but so does death by drowning. So there is a strong correlation between ice cream sales and death by drowning. Therefore, ice cream causes drowning. Now, is that a sensible correlation? Well, no, that's not a sensible correlation. They're just things that both happen a lot more during summer. So, yes, using your data, coming up with a proposal, a prediction, whether things correlate, it's fantastic, but really you then have to look at it and say, well, are there any other, is there any other research which would back this up, or is it just nonsense? So correlation does not mean causation. Just because two things correlate does not mean one thing causes the other. Okay, let's have a go at 15D.